I'm Anil Kumar. Welcome to my series on combinatorics. We'll discuss what is permutation and we'll take up many examples relating to different situations which you find in test papers. We'll look into what are distinct items, means unique, totally separate, identifiable. We'll also look into cases where we will have some identical items to find the permutations. When we say to find the number of permutations, it really means the arrangements in an order, right? That is what it means. And so we'll look into cases where we'll discuss arrangements in an order, but everything placed in a row. It can also be placed in a circle. So we'll take both the cases and see what is the difference between the two. We'll see what happens when arrangement of only some items out of all the given items is to be considered. And then we'll look into the formula for permutation and do related algebra based on the formula of permutation. We'll choose from several sets of identical items, and that becomes a very general case for permutations. And in that case, you will notice that a permutation of n distinct items taken r at a time is an arrangement of r of the n items in a defined order and is written as NPR, right? So this NPR is the notation which we are writing here as NPR. It could be written as NPR or PNR. It means that the total number of items are n, out of which we are taking r items and arranging them in an order. So whenever the order is important, we will be doing permutation. We'll talk about combination in another video where order is not important, where we are choosing in a group, so the order is not important. So these are the two things which are very critical to understand to do most of the questions based on counting principles. So the formula for PNR is equals to n factorial, where n is the total number of items which we need to consider, and r is the number of items which we are taking at a particular time, right? If they are arranged in a row, for example, taking picture of family having 7 members, for example, n will be 7. Since all are taken together, then the answer is only n factorial. N minus r will become 0. Now 0 factorial is also 1, which is known to you. Perfect. Now if we want to consider the cases of arranging few books on a shelf in a row, let's say you have 20 books and you want to arrange only 10 of them. In that case, R is going to be 10. And we could have an example where out of these 20 books, they belong to different subjects, but they are distinct books. Then we'll consider another formula, which will be based on identical items, right? I hope you're getting the concept. Now, there are some special cases where we want some particular letters or words to be separated and some inserted in between. And a common example will be separated and together. We'll just consider vowels as a case, but it could be extended to many situations, right? So, for example, here we have a word which is like Mississippi. And that's a very popular word to arrange in many different ways. And you can see there are many letters which are duplicate here, right? So we'll see how to arrange such words. Let's begin with the basics. So let's talk about what permutation really is. Permutation is number of ways in which you can arrange the letters in my name Anil, for example. So you could arrange many things, anything rather, right? But they should be distinct kind of thing. Okay, so letters in Anil are A, N, I, L. So we basically want to arrange these letters, right? So A, N, I, L. Perfect. Now, they can be arranged in so many different ways. So one way is you just arrange them and get different words out of it. These words may or may not have a meaning. That's not important. But what is important here to understand is in how many ways can you place these letters, right? Taking all four of them in every case. So you can write starting with A, next could be ANIL, right? And then you can start with so many combinations with AN. So every letter will give you many ANIL, ANLI, and then you can start with A and next letter could be L, and then NI, and you can flip IN. Now these two are different words, correct? So they'll be counted as different words. And similarly, if you write all the combinations, you get what? You get 24 combinations as shown here, right? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. 8 times 3, 24. Now, the same thing can be done in a much easier way by thinking like this, that you have four spaces to fill, right? This is extremely important to understand. You have four spaces to fill. Now, in these four spaces, you have to place one of these letters, right? So there are four letters which need to be placed. So the options here are, how many options do you have? This is what you have to look for, right? Options here are four, right? Since out of these, you can choose any one of them. Now, once you make a choice, let's say you choose I, for example, in that case, how many are left? Now, we know there are three left, right? So we have choice from three, and when you choose another element, let's say you choose another element, in that case, after that, how many are left? So that is what you have to see. Well, two are left after that, and once we make another choice, right, in that case, how many are left? Well, one is left, and that's what you get. Now, these four choices were independent, right? They were in order. Do you see that? They were in order, right? Now, in a particular order, and we followed some steps, correct sequence. So you can now apply the multiplicative rule of combinatorics, which you learned in the very first chapter, which was the introduction. So the answer should be product of these three. So the answer is 4 times 3 times 2 times 1. And that's how you get your number of options, which becomes 4 times 3 is 12, 12 times 2 is 24. So you get the idea. So without actually placing all of them as shown here in the table, we could actually just count by filling up spaces. So this is the most powerful technique to write down our answer, right? Especially when they are big numbers, you understand? So for example, if I have like 100 items and if I have to place all 100 by filling up spaces in a row, think like this, right? In that case, the answer will be 100 times 99 times 98 times 97 and so on till 1, as you can see here. So we do have factorial notation. So the answer becomes 4 factorial. You get the idea. So if you have 100 items, in that case, it will be 100 factorial. 100 distinct items to be placed in a row, all 100 of them at one time. In that case, one by one, when you're placing on the positions, in that case, then you'll have 400 factorial answer. Do you get the idea? Perfect. This is what we're talking about here. So let's go through it. Writing all the options may not be easy for longer words. Here is a strategy to solve such situations. If we are interested only in the number of all the possible options, think four spaces to be filled with letters A, N, I, and L. So these were the four spaces which we filled, right? We have four options for the first space. Once that is filled, we have three options for the second place, and then two for the third place and one for the last space. Applying the counting principles, 4 times 3 times 2 times 1, which is 24, is the number of ways of filling this. So you can put these in a boxes, for example, here. Perfect, as I was saying. In short, arranging n objects in a row, we have n times n minus 1 times n minus 2 till 1, right? So this could be written n n factorial, right? We can be written this as n factorial. So that is what it is. So what you learned now here that normally if you're putting all the objects and they are distinct, right? Like A N I L, nothing repeats here. In that case, the permutation is arranging of elements in a linear row. And in this particular case, when you take them all, in that case, it is n factorial. Simple answer, right? Now let's extend with few more examples to understand the situation. In example 1, we are going to take some distinct items taken all together as we did in the explanatory example. Now here, find the number of different 5-digit numbers that can be formed using the digits 2, 3, 4, 5, and 6 without repetition. If, now these are different conditions, and that is how a test or examination question is designed. So you can see 2, 3, 4, 5, and 6 are 5 distinct digits. This is important to understand, right? So we've taken distinct, right, items taken all together. So we are arranging all 5 of them. Now, in that arrangement, we have different restrictions. Let's first talk about no restriction at all. So as we have just learned, the answer should be 5 factorial. Think about the spaces once again, right? So think about 5 spaces, 1, 2, 3, 4, 5. And what you can do here is you have out of these 5 numbers as a choice. Once you take one of them, you're left with 4 and then 3, 2, and 1. Just multiplying them, right, using the product rule, we get our solution, which is 5 factorial and is equal to 120. You can always use the calculator to calculate such answers if in the test calculator is required. Okay, option B. Question B in this situation is even and odd numbers alternate. So like like we wrote here, right? The sequence of numbers we have to choose so that even numbers and odd numbers alternate. Well, let's look into the even numbers. In this particular case, what are the even numbers we have? Well, the even numbers are 2, 4, and 6, correct? And the odd numbers in this case are uh, 3 and 5. So we have 3 even numbers and 2 odd numbers. So that really means that we have to place even number first, only then they can alternate, right? So we have even, odd, and even. As all are distinct, let's call even 1, even 2, even 3, right? And odd 1 and odd 2. So 2 different odd numbers, 3 different even numbers to be placed. What you're looking into a situation where they alternate. So that becomes the situation. Now, see in this situation, how am I going to produce the total number of items with easy calculation? So let's fill up even numbers first, for example, and then let's try to fill up the odd numbers in the spaces in between. That is how you have to work when you look into separated cases. You get the idea, right? So this is what we are going to look into. So they alternate also, right, as shown here. Now in this particular case, out of 3 even numbers, you are using all 3 of them. So how many cases are there in the first case? For even numbers, we have 3 factorial, 3 times 2 times 1. And for inserting these 2 odd numbers in between, we have 2 factorial ways, right? So there are 2 numbers, 3 and 5. You could place 3 here and 5 there, or the reverse 5 and 3. So in all, the result will be 3 times 2 factorial. And so we get our answer, which is 3 times 2 factorial. 3 factorial is 3 times 2, which is 6, and 2 factorial is 2. So we get 12 as our answer. You get the idea. That is how you have to answer such a question. Now, question number C is even numbers are together. Now, this time we are only restricting ourselves to placing even numbers together. So, odd numbers could be either side, as you have seen. Now, you could treat this as one block, you understand? So even numbers are together. So we have, for example, we can write like this is one block now. So think about arranging three items in a row. So how many choices do you have? Well, you have 3 times 2 times 1, or 3 factorial as the choice, and that is what it is. Now think about the three even numbers themselves. Now if this is a block, for example, right? If this is a block with three numbers, correct? So let's say the three numbers are 2, 4, and 6. Let me write down. Okay. So in that case, let me change and rewrite this as 2, 4, and 6. Now 2, 4, and 6 could be arranged in many different ways. How many ways? 3 factorial ways. 3 times 2 times 1. And with each way, we could place here either 3 or 5. Perfect, so 2 ways. So that is how we're going to answer. So we have 3 factorial times 3 factorial ways, and we get 36 as our solution. So I'd like you to understand this process and then move forward, since these are very common examples which you could see in a test paper. The last question here, variation, is even numbers are together and odd numbers are together. So basically we have now two groups. Now these two groups, one after the other, could come, and so in that case we have 2 factorial as the group, right? Now within the group we have three even numbers. So 3 factorial for those 3 factorials for those three even numbers, and 2 factorials are the number of arrangements which the two odd numbers can go through. So multiply all of them. Since these are all independent, distinct, sequential combinations which can take place, therefore they should be multiplied using our combinatorics fundamental rule. So when you multiply, you get 24 as your answer as shown here. So once again, when we're talking about putting even numbers and odd numbers together, it is basically two blocks arrangement which gives you 2 factorial. Now within those three even numbers, 3 factorial are the ways to arrange these even three numbers, and for odd, the two numbers, there are 2 factorial ways to arrange them. Total arrangements are the product of 2 factorial, 3 factorial, and 2 factorial as shown here. Do you understand? That is how it is to be done. Remember, in these cases, all the 5 numbers were distinct and they are not to be repeated. Okay, let's move on and now understand a few more things, which is we're not talking about example 2, which says distinct items taken all together. Okay, so in this case, when we say taken all together, in this particular case, find the number of different 6-digit numbers. Now we have just changed the example. Instead of the 5-digit numbers which we took last time, we are saying find the number of different 6-digit numbers that can be found by using the digits. The digits are 0, 1, 2, 3, 4, and 5. Okay, so we included a 0 in number of digits, right? 0 is a valid digit. Now there is no restriction, but what we want is to fill up 6 spaces, right? So we need to fill up 6 spaces. 1, 2, 3, 4, 5, 6. Now remember, you cannot start with 0. If I start with 0, in that case, we have only a 5-digit number, right? You see that? That's a key to understand, and that's the major difference between this example and the previous one. So you cannot start with 0 to form a 6-digit number given these 6-digit numbers where the digits cannot be repeated. You get an idea. So the options to fill up the first space we're left with is only 5, right? So there are only 5 ways of filling the first position. Since I cannot write 0 there, does it make sense to you? Perfect. Now out of 6, we have already taken 1 away. So we're left with now 5. Now in this case 0 can be placed anywhere, right? So we are left with 5 and then 4 and then 3, 2 and 1. So the options will be as shown here, product of all of them, which gives us 600 as our answer. You get the idea. So that is how it is to be done. And remember, when you have digits and you want a 6-digit number, then 0, 1, 2, 3, 4, 5 is not a 6-digit number, it's a 5-digit number, right? Okay. So now let's take another example. It says, how many 6-digit numbers are even in part A, right? So, some are even, some are not even. Now, in that case, how should you be doing it? Think about it, answer this question, and then look into my suggestion. I will start with making these six spaces, right? 1, 2, 3, 4, 5, and one more 6. So we have six spaces to fill. When we are saying even numbers, it means we are restricting the last position. Now, earlier we restricted the first position since 0 could not be placed. Now, in this particular case, we do have a restriction in the last position. Now, the restriction in the last position is that it could be out of the given digits either. So, let me say the last position restriction is that here you could place either 0, that will make the number even, 2, or 4. So these are the three options for the last position. Now in this case, you will also notice that if I place 0, then for the first position, I have no restriction because 0 has been placed and then I'm left with the other 5 to be placed. However, if I place 2 in the last position, then in the first position, I have two different cases, right? Now, I cannot put 0. So two numbers drop out from the first position. You get the idea, right? So therefore, we have to look into different ways of putting up the last digit. And based on that, we need to answer our question, correct? So numbers ending with 2 and 4 will give rise to one set of combinations, and number ending with 0 will give us another set of combination. So we have different cases. So let's call them case 1, right? So case 1 is when the last number is 0, right? So we put 0 there. So if I put 0 here, in that case, we are left with 5 digits. So we could put any one of them. So 4, 3, 2, uh, 5, 4, 3, 2, 1 will be the other numbers. And what we get here is 5 factorial cases. Perfect. Now, on the other hand, if I place instead of 0, if I place either 2 or 4, right? 2 or 4, right? One of them. In that case, I cannot place 0 here. Perfect. So I have only 4 options in this particular position. Only when I place a number which is not 0 in that position, in that after that I can put any other number. So those will be 4, 3, 2, 1. You get the idea. So those are the options, and therefore the result will be, for those two cases, we have 4 times, because there are 4 choices, times 4 factorial, right? So 4 times 4 factorial, and 2 times because we have two numbers to place there, either 2 or 4. Combining them, we get our result as shown here. Perfect. So we have 5 factorial plus, in the case 2, we have 2 times 4 times 4 factorial. And that gives us as 120 plus 192, which is 312 total choices. You get the idea. So we have done two different cases. Perfect. Rather, you can call them three different cases also. So in the second case, we took two options, 2 and 4 at the last position. Correct. So that gives you the combination of addition also with multiplication, right? So you can see that the second principle, when we are talking about mutually exclusive cases, perfect. So either you choose 2 or 4 for the last position, or you choose 0. These are mutually exclusive cases. So we can have a combination of multiplication, so multiplicative and additive properties, right, which you studied in the very first unit. So I hope you understand this concept, combinations being applied. Now let's look into the next example, which is permutation of R items from n distinct items. So till now, like we had 5 numbers, we're taking all 5. We had 6 numbers, we're taking all 6 numbers. Now we'll not take all, but we'll take some of them. Okay. Now the question is, find the number of ways of selecting president, vice president, and secretary from a group of 8 members. So we have 8 different distinct members, out of which we have to select for only 3 different positions. So selection is done of 3 out of 8. Not all of them will be selected. Do you see that? Well, all could be selected, one for 3 different positions, so 3 will be selected finally. So in this particular case, we have a choice to make, but we have only 3 particular positions. Do you see, right? So this is being selected from 8. So definitely in the first position, we have a choice of any one of those 8 could be the president, for example. But once the president has been selected, that person is out of our list. One position cannot be shared by 2 people. So now the second position, we're left with 7 people to choose from, and then 6. So the answer will be 8 times 7 times 6. So I hope this process is absolutely clear. Now this 8 times 7 times 6 is also written here as the answer with the complete explanation, which you can go through. Now, now we'll actually look into how do we write this particular case. Now when we are selecting 8 from a group of 8, we say 8p3. 8p3 means selecting 3 out of a total 8. So 8 permutation 3, that's what it means. Here the order is important, and so we could multiply them. They are done in a particular sequence. Perfect. So 8p3. Now we got the answer as 876. Can I write this in factorial form? Let's see this, right? So what we have here is 8 times 7 times 6. Imagine that we multiply this by 5 times, 4 times, 3 times, 2 times, 1, right? And also divide by 5 times, 4 times, 3 times, 2 times, 1. In that case, clearly, I could write the numerator as 8 factorial and the denominator as 5 factorial. You get the idea. So once I can write this, then 5 factorial is 8 minus 3, right? So we can write this as 8 factorial over 8 minus 3 factorial. So that gives you an idea. How do we connect the NP3, NPR with the final result? So here is the connection. If we have to choose from n r elements, in that case n factorial divided by n minus r factorial is the number of ways of this choice to be made, right? So that's what we'll conclude here from this particular example. A permutation of n distinct items taken r at a time is an arrangement of r of the n items in the defined order. The notation NPR is used to represent number of permutation of R items chosen from n items. So NPR is written, which is n factorial divided by n minus r factorial. So this is extremely important formula, very powerful one, which can solve most of the problems based on permutation. Perfect. Now, next example here is, now we'll work more on the NPR itself. So, permutation of n distinct items taken R at a time. There are n ways of choosing the first item, right? And n minus ways, n minus one way of choosing the second item. So what we're trying to, we are generalizing the case. Let's say these are our cells, right? These are our n cells. Perfect. So we can fill up the first cell in n different ways, correct? Once we choose one of them, then we are left with n minus 1, and then again we are left with n minus 2, and at the end there's only one possibility. Using the product rule, right, we can multiply them all, and that is taken n at a time. So this is npn, right? Do you see that? So in case of npn, we get n factorial as our answer. However, if we have r items to be chosen, right, not n, right? So if we have r items to be chosen, that means, let's talk about the second case when we're talking about npr. So definitely you have n choices, and then you have n minus 1 choices and n minus 2 choices, but at the end you may have n minus r plus 1 choices, correct? So that becomes your number of order in which you can choose. So in general, it could be written as n factorial over n minus r factorial. Does it make sense? This is what we're trying to explain here. So now let's look into it. There are n ways of choosing first item, n minus 1 ways of choosing the second item, and so on down to n minus r plus 1 ways of choosing the rth item. Using the fundamental counting principle, NPR is therefore equal to n times n minus 1 times n minus 2 till n minus r plus 1. Now, NPR in the factorial form, the whole thing you could multiply and divide by n minus r factorial, and so the formula reduces to NPR equals to n factorial divided by n minus r factorial, as we also discussed in the last example. So I hope this concept is absolutely clear. Now let's take the next example, which says you need to prove that 0 factorial is 1. It's another very interesting case, right? So the number of permutations of n distinct things taken r at a time, which is npn, is n factorial. We have learned that, and this is just a summary. The number of permutations of n distinct things taken r at a time is n factorial over n minus r factorial. Perfect. Now let's get to the solution of the question. We know that npr is written as n factorial over n minus r factorial. Npn is written as n factorial itself, which is n factorial over n minus n factorial. So what do you see that? So I wrote npn as equal to n factorial over n minus n factorial. Correct. So n minus n here is 0. So we have here n factorial over 0 factorial. Correct. But what is npn? We know npn is n factorial. Now n factorial is equal to n factorial over 0 factorial. You could cross multiply and write 0 factorial equals to n factorial divided by n factorial. Now we know this right side is 1, and clearly we have shown that 0 factorial is 1, right? So we have shown that 0 factorial is also 1. So that is a simple proof that the value of 0 factorial is indeed 1. Now here is another example where we are working with the numbers, the algebra with factorials, and the permutation definition itself. Now the question here is to solve for n, and the equation is, let me write it a bigger equation. We're writing this as n minus 1 p3 is equals to 12 times n minus 1 p2. So if that is the equation given to us, we need to solve for n, right? So I'd like you to pause the video, answer this question, and then look into my suggestions. So let's begin. So, well, this is n plus 1, sorry. N plus 1 p3 equals to 12 times n minus 1 p2. So that is to first left side is we are choosing 3 when a group is given to us of n plus 1 distinct items, and that is equals to 12 times the choice which you're going to make with a group n minus 1, and you're taking 2 out of them. Okay, so on the left hand side, from the very definition of NPR, we can write n plus 1 factorial over n plus 1 minus 3 factorial, right? On the right hand side, using the same definition, 12 times n minus 1 factorial over n minus 2 plus 1 factorial. So that is how we could write the number of in the permutation in the form of factorial. Now we have to simplify these, right? So in the denominator, we will just 1 minus 3 is minus 2, so we get n minus 2. And on the right side, minus 2 minus 1 gives me n minus 3. Now, looking into these terms, what we could do is, we could expand n plus 1 factorial, writing this as n plus 1 times n minus 1 times n minus 2 factorial. Perfect. So this n minus 2 and n minus 2 can further be cancelled. So we can cancel these. On the right hand side, it is 12 times n minus 1 times n minus 2 times n minus 3 factorial, and n minus 3 in the denominator will now cancel. So that will lead to the equation n plus 1 times n minus 1 equals to 12 times n minus 1 times n minus 2. As you can clearly see here, n minus 1 can now be cancelled. And so we have a much simpler equation, n plus 1 times n equals to 12 times n minus 1. So that is the quadratic equation which you need to solve. So that becomes the quadratic equation. Bringing the terms together, factoring them, gives us the solution of n as 8 or 3. So we have two solutions for this particular situation. So n could be 8 or n could be 3. So that is how such equations will be solved. So I hope the whole concept is absolutely clear. Let's move forward and take example 7. So I've taken many examples, all the example types which are expected in examination from just permutation are being considered here. Now in another video we'll discuss about combination, and in the third video after that we'll have both mixed up, permutation and combination, to really check your skills of understanding this particular topic. So keep that in mind while moving forward. Okay. Now, example 7 is all distinct grouped items arranged in a row or a circle we began with, right? So we'll understand a very important concept here. So the case here is I have 14 different mathematics books, 7 different physics, and 5 different chemistry books, right? So these are the total books I have. 14 of one type, right? It's a 14 mathematics book. And then we have 7 physics books, and let's say 5 chemistry books. So if I add them up, how many total books do I have? Well, 11 plus 5 is 16, 6, 1, 26 books, right? So these are the total number of books, right? Okay. Now, subject-wise, we have 14, 7, and 5. Now, we'll now consider different cases of arranging these books in a shelf in a row, right? So, the question here is, how many ways can I arrange them in a row on a shelf? So basically, we have 26 spaces to be filled, and you can choose any one of them. Beginning with 26 is the option. So 26 factorial is your answer. Part B. How many ways can I arrange them on a shelf if I want to group them together subject wise? So I want the maths together and I want the physics together. So I have to just group them so that we have the same groups. But these three groups which are formed can be placed, in any order. So for that we have three factorial ways, right? Arranging them. And within these, there are 14 mathematics books. These 14 books could be shuffled in 14 factorial ways. 7 physics books could be shuffled in 7 factorial ways, and 5 chemistry books can be arranged in 5 factorial ways. So multiplying them all together, we get our answer, which is a typing error here. So you need to calculate this answer and write it down, correct? So I think you can do that. So we have 3 factorial ways, right? So you could just calculate this answer, 3 factorial times, or we have 14 factorial times, you can use the calculator for this calculation, 5 factorial. And when you multiply them all, you get a very big number, which could be written here as your answer, correct? So that is what you have to do. So there is a typing error, so just write this much. That will be good. Okay. Now, part C. How many ways can I arrange them in a circle on my spinning circular table? Now, remember, when you are arranging in a circle, let's say we have 1, 2, and 3, right? So these are your books. So let's try to understand the situation. And when you arrange them in a circle, we have, let's say, maths, physics, and let's say chemistry. So when you arrange them in a circle, you could have one combination like this, and then you can have a different combination by changing these two orders. So you could also have like maths, chemistry, and physics, correct? So you could do that, and then you can again change the situation. But what you'll observe here is that when you make the situation as the third one, which is now swapping maths and physics, so you get physics, chemistry, and maths. So when you write physics, chemistry, and maths, you see you did write a different combination, but this is again the same as maths, physics, and chemistry. So you can see that these two combinations are exactly same. So when you're putting on a circular table, you have a situation. Since the order doesn't start from one point and end, there's a continuity. So in that particular case, what really happens is you have to fix some number. So you have to have a fixed point. So you have to fix a number and then arrange the others to get the real combinations. Otherwise, there's a duplication, as you can see here. Perfect. So this is kind of very important while you are arranging them in a particular circular manner, right? So therefore, these are cases which are different from what we will do when we put them in a row. So let's go to the question once again. How many ways can I arrange them in a circle on my spinning circular table? Well, we need to fix one book and arrange the others. So out of 26, one has been fixed. Now we have 25 factorial ways. Do you understand? So one less, right? So there were 26 books. We have 25 factorial ways. Now, another variation to this is how many ways can I arrange them in a circle on my spinning circular table if I want to group them as per the subject? So, as we took earlier, but this time in a circular way, we have now three different groups. Now, in three different groups, you have to fix a group, right? So, you have 2 factorial, but within the group, you'll have all those arrangements to be made, which is 14 factorial times 7 factorial times 5 factorial. So the product of this with 2 will give you the answer. This makes sense to you. Correct? So when you arrange them in circular, there are lesser number of ways. Okay, with that in mind, let's move forward to example number 8, which is working with numbers once again. Right. So we have now a question which says, how many 5-digit numbers will contain only odd digits? So we have 5-digit numbers. How many 5-digit numbers will contain only odd digits? So that is the question. Now, when we say contain only odd digits, so digits are what? 1, 3, 5, 7, and 9. So we are basically working with these 5 numbers, right? So now here we are saying how many 5-digit numbers will contain only odd digits. So clearly, in this particular case, we could choose in this position 1, 2, 3, 4, 5, any one of these 5, right? So here we are including repetition, okay? So there are 5 odd digits. The numbers can also be repeated because we have not put any restriction. So in these digits, we could write 5, 5, 5, 5, 5 as also a number. Perfect. So since we have 5 choices to make for each item. So we have 5 times 5 times 5 times 5, which is 5 to the power of 5 as our answer in this particular case. Correct? Now, part B. In how many ways can you select two distinct integers from a set which is 1, 2, 3, 99, 100, all the numbers from 1 to 100, so that the sum of two numbers is even? So now we want to select two numbers whose sum is even, right? So that is the question now. So we have to do distinct integers, means you cannot repeat the same thing, right? We have a distinct integers. In the previous case, that word was not there. So we could repeat any digit. Now to make 2, sum of 2 as even, you have to take either both odd or both even, right? So we have a choice here and we are saying both odd or both even. They will add up to even numbers. That is what we have to think about. So here is your solution. So numbers cannot be repeated. That is given in the condition itself. So for some, both will be either even or both will be odd. You get the idea, right? So, but if you choose one even number, you cannot choose the other even number, right? So we know there are 50 even and 50 odd numbers. So if you choose one, then you have a choice of 50 for the first position, and taking away 1 will leave with 49. Now that could be uh, done with first, let's say, odd series, and then you can also work with even series, same combination, correct? So the total cases will be product of 50 and 49 times 2 as shown here. So that is how you're going to get your solution. I hope the logic is absolutely clear And this is what is important to understand as you go through my examples. Now, part C is the car number plate in Ontario has four alphabets followed by three numbers. Find the number of possible car number plate combinations. So, well, now look here. So, we have four alphabets. So, one, two, three, four. These are the alphabets, followed by three numbers. These are the numbers, right? Do you see that? So, in alphabets, we have 26 combinations. Okay, cool. So we have 26 choices times 25 times 24 times 23. As far as the numbers are concerned, so we have a choice 10 numbers. Can I place 0 here? As far as the car number is concerned, 0 can be placed, right? So we have 10 choices here, 10 choices there, and 10 choices. 011 is a valid number, right? 000 is a valid number for a car number plate. So remember that. We are not talking about a three-digit number, right? So we have a choice which is 26 to the power of 4 times 10 to the power of 3. Next question based on such related number type of questions is what is the highest power of 2 that divides evenly into 100 factorial? So that is another very interesting question, which is keep the factoring 2 from the even numbers. So how do we do this? What is the highest power of 2 that divides evenly into 100 factorial? Well, how do we figure this out? Well, there's a strategy. So out of these 100 numbers, we know we have 50 even numbers, correct? So you can factor out 2 out of those 50 numbers, correct? So we have, let's begin with, so we have 50 even numbers. So from these 50 numbers, if I take away 2, right, then we are left with 25 even numbers, correct? Half of them will be odd when you multiply those 50 numbers. And then from 25, if I take away 2 as a factor, I'll be left with 12 even numbers. And then from 12, if I factor out 2, I'll be left with 6 even numbers. And from there, if I factor out 2, I'll be left with 3 even numbers. And then if I factor out 2, I'm left with 1 even number. So basically, this gives me 27 2's which we factored out. And so the answer is 2 to the power of 97. Sorry, 97. When you add a 50 plus 25 plus 12 plus 6 plus 3 plus 1, you get 97. And so you get 2 to the power of 97 as your answer for this particular situation. Is that clear to you? Right? So what I'm trying to say here is very important to understand. So those 50 numbers, for example, will be, let's begin with the numbers and let me give you exactly what we are trying to say. So 98 and then 96, right? And so on. And then we have the numbers 4 and 2, correct? Now out of these numbers, what I could do here is I could factor out 2. As soon as I factor out 2, then we have half of these numbers coming up, right? So 49, 48, correct? And then we have the numbers will be 2 and 1 when you divide them. But remember, these are the 50 numbers which we are talking about. Once you factor 2, then these are the 25 numbers which we are talking about. Do you see how we have got in this 2 50 times? That is what we mean here. Once you factor and then again factor, we get 25 numbers after this factoring. So if you continue this process every time, half the number will be even numbers out of your set of numbers. And so we can add them in a sequence and get the answer as 97. So 2 to the power of 97 is the highest power of 2 that divides evenly into 100 factorial. Does make sense to you? This is a challenge question which you can find in the test papers. Let's move on and take the next example, example 9. Permutation with some identical items, right? So till now we had distinct items and now it is all over a shift to where some items will be identical. Well, we did deal with some identical items also, but in a group. Let's look into these cases one by one. How many four-digit numbers can be written from the set 1, 2, 3, 3? Do you see that? Now the number 3 and 3 are identical. That means you could repeat 3, right? But if I write 1, 2, 3, 3, and if I change the position of 3's, the number is the same number. You get the idea, right? So that makes huge difference. So we'll now talk about permutation with some identical items. Case 1. How many four-digit numbers can be written in the set 1, 2, 3, 3? Now, as you can see, since you have repeated 3, so uh, in this particular case, what really happens is the answer. Out of 4 factorial combinations which you began with, uh, 3 positions are being repeated twice. So those will be same, and so we have to deduct them from our list. So out of 4 arrangements, 12 are actually different because of 2 threes, and the answer will be 4 factorial over 12 factorial, which we can write as 12. You get the idea. So when you're repeating, in that case, there are duplications, and we have to take away those duplications. Okay, now we'll actually come up with a general formula also, which is n factorial over a factorial, b factorial, c factorial, where a, b, c are the number of repetitions. Okay. Question B. How many permutations are there of the letters in the word Mississauga? Now, in Mississauga, we have many letters which are being repeated. Do you see that? So, for example, in Mississauga, there is one M. So, let's split this word. So, we have M and then we have I. How many I's are there? So, we have number of I's are 2. Okay. And then we have S. Number of S are 4, right? So we just counted 4, and then we have A, which is 2, right? So we have 2 A's. Correct. And then other letters are 1 each. So what is important to note here is that there are 11 letters in Mississauga, right? With 2 I's, 4 S's, and 2 A's. They repeat. And so, when we are saying how many permutations are there of the letters in this word Mississauga, since there are 11 letters, 11 factorial comes in the numerator. Now, we have 2 I's, 4 S's, and 2 A's. So 2 factorial, 4 factorial, 2 factorial. We'll divide this. Those will be the duplicate. And when you use the calculator and calculate, you get the answer as 415,800. So that is how it should be done. So when you are repeating, in that case, those repetitions will divide, right, the number of combinations. Perfect. Now, here is part C, which is find the number of arrangements of the letters in the word class where S's are separated, right? So we want S's are separated. Now we could do this in an indirect manner also. So one method could be find all the cases. So we find the total number of ways of arranging CLASS. S is being repeated, so it will be 5 factorial over 2 factorial. 2 factorial is because of the 2 S's. Now, the number of ways where S's are together, we could take them away. So treat S as one group. So we are left with only 4 groups, C, L, A, and one with 2 S's. So take away 4 factorial ways, and that gives you the one where S's are not together. So if there are only 2 numbers separated, in that case, we could follow this particular method. And here is a note. This method works only with, for example, 2 of one kind. Right. So with that, we get this answer. I hope that makes sense. So what we have learned here is that the permutation of n items with a identical items of one type, b identical items of another type, and so on is n factorial divided by a factorial, b factorial, right? That's a very important formula. So these are the total number of items, and these are kind of repetitions, right? So a factorial, b factorial, and so on. Any number of repetitions could be taken care of, right? So in Mississippi, we found, oh sorry, in Mississauga, we found 2, 4, and 6 numbers for I's, S's, and A's. Okay, 3 more examples to go. We are almost at the end. 3 more examples to go. And that gives you wide variety of examples to work with. And I hope that will help you to prepare for your own test. Example 10 here is number of paths. Well, we dealt with this in Pascal's triangle also, if you remember, right? Now here is a faster way of doing it. The question here is, find the total number of distinct paths from the point A to B, traveling only south or east. So we are given 2 points. A is right there and B is at the end. So those two corners, correct? So we have to now find the distinct paths of going to the from one end to the other. Now here you can see you can only travel south or you can travel east. So if you go south, we have 5 different steps to go to south, for example. So from here, 1, 2, 3, 4, and 5, right? So those are the 5 steps when you go to south. So so this is 1, right? Then 2, 3, 4, and then south, 5. So there are 5 steps to go south. As far as east is concerned, you have how many? 1, 2, 3, 4, 5, and 6. Then you reach at B. So you have 5 going towards south and 6 going towards east. So total is 11 steps. So 11 comes in the numerator since there are total steps of 11. Now going south, going south, going south, those 5 different options. So you could go either way. So 5 factorial because they are being repeated and 6 factorial for going east. And that is how you get the answer which is shown here. Is that clear to you? So it becomes so simple if you just figure out and how many ways are you going south and how many ways you're going north. You can just calculate rather than rather than putting in the numbers and adding them up, right? Especially if there are long blocks to work with, this is much simpler. Question number 11 here is very elaborate. Now this time we're looking into permutation with some identical items. Now this is extremely important question from test point of view. So we have taken different types of scenarios. One is a coin is tossed 8 times, correct? In how many different orders of 5 heads and 3 tails could occur? Now that means you can think about 8 times the event is being done, which is tossing the coin. So 8 factorial. Now we want 3 heads, right? That means like filling up. 1, 2, 3, 4, 5, 6, 7, 8. Now we could have heads at 5 heads. So we could have heads at any different positions, right? No particular order, but we have to have 5 of them, for example. So once you fill these heads, 5 out of 8, then we are left with 3 different positions to fill up the tails. That is how you could understand this particular situation, right? So tails, now therefore, since heads and tails are kind of repeated same numbers, therefore we'll have 8 factorial over 5 factorial 3 factorial as the answer in this particular case, right? Total number is 8 and out of which 5 heads which are kind of identical items, right? H you have to fill in. It's not number 1 2 3, correct? Different, the same number. And so that becomes the solution of our question, right? So that gives you one. B is, how many different ways can you arrange the letters in bananas if the N's and B's must be together? So when you say N's and B's must be together, you can make one block with N's and B's. So in this we have only one B and two N's, so we have that one block. All of the letters are kept separate, A, and then one block and A. So we have 1, 2, 3, 4, 5. So in 5 ways you can arrange them, but in this 5, A is 3 times, so we'll divide this by 3 factorial. So that explains why we have 5 over 3 factorial, just to look into the arrangement of these blocks. Now, within the block of banana, we have 3 elements to be arranged, and out of them, 2 are n's. So 3 factorial divided by 2. So the product of that will give us the answer, which is 60 in this particular case. Correct? So that is how you're going to answer such a question. And now let me take the last part of this, which is how many 7-digit even numbers less than 300,000 can be formed using these digits, right? So we are now interested in even numbers. That means ending with either 2 or 6 from the given choice. And less than 300,000 means that the starting number could only be 1 or 2, right? Those are the cases. So think about it. So even numbers less than this starts with 1 or 2, right? And ends with 2 or 6 from the given choice. So that gives us many different cases. So you have to work on cases. So case 1 is when you're starting with 1 and ending with 2. Correct? Because you could start with 1 or 2. So case 2 is starting with 1, ending with 6. You could end with 2 or 6. So those are two different cases starting with 1. Then we have a case where starting is from 2 and then again a case starting with 2 but ending with 6. So we have four different cases here as written, correct? So four cases to work with. In each case, we'll find the permutations. So in the first case, when you start at 1 and end with 2, the number in between to work with are 2, 3, 5, 5, and 6. Since 5 repeats, we'll divide by 2 factorial, right? So 5 factorial over 2 factorial is the number of permutations for this case. In case 2, when you begin with 1 and with 6, we have 2, 2, 3, 5, 5 to be placed in the 5 positions in between. And these 5 positions have repetition of 2 and 5. So we are going to divide by 2 factorial and 2 factorial, the number 5 factorial, to get all the permutations. Now in case 3, beginning with 2 and ending with 2 leaves us with two duplicate 5s in the 5 options. So 5 factorial by 2 factorial, which is 60, is our answer for this particular case. Now the permutations when you begin with 2 and end with 6 will lead 1, 2, 3, 5, 5 as the choices for the middle 5 numbers. So 5 factorial by 2 factorial, which is 60. Adding all these options will give you the answer, which is 210 ways in this particular case. I'd like you to go through this condition once again, as this is one of the most popular questions asked in this particular topic. Here is the last example where we'll talk about keeping some elements together and some separated. Many different ways of asking this, like in a group, there are two friends, they want to be together or separated, correct? So those could be some cases. But I've taken a very complicated word with which is very popular also. The word is Mississippi. Now, Mississippi is very interesting. It has 11 letters, 4 I's, 4 S's, and 2 P's, right? So that is the beauty of this. We have three numbers, which alphabets which repeat, 4 I's, 4 S's, and 2 P's. Since there are 11 numbers, and first part is very simple, find the number of arrangements of the letters in Mississippi, 11 factorial, divide by 4 factorial, 4 factorial, 2 factorial. You get a number as your answer. The second part is, in how many of the above arrangements are S's together? So we have to now see putting S's together. So make a block with all the 4 S's, and then out of 11, since we clubbed 4, we are left with 8 blocks, you can say. So 8 factorial is what we get. Now within those which we are left with, we have 2 I's and we have about 2 A's, right? So we'll divide by 4 I's rather. I should write, there are 4 I's. So we divide by 4 factorial for I's and 2 A's, so 2 factorial with A's. So then we get 840 combinations. Well, since these are S's together, their permutations do not really add. 4P4 is 1. Now, C is find the number of arrangements where S's are separated. Now we want S's to be separated. Well, earlier we did S's together. If you do total choices, take away together, you will not get the right answer, because separated means even 3 cannot come together, right? Right? 2 cannot come together. Those makes it so many other combinations, all separated. So how do we do such a question? Well, separate out all these S's. Now you're left with 8 numbers, 7 to work with, right? So if you take away these 4 S's, you're left with 7 other letters. Let's see how we can arrange these 7 letters. So 7 factorial over 4 factorial and 2 factorial, 4 i's and 2 a's, right? So that is how we get one number of arranging all these letters except s's. Now we see how do we insert these s's in between? Only then they can be separated, correct? So we see how many positions are there. 1, 2, 3, 4, 5, 6, 7, and 8 positions are there, and we have to fill in 4 s's. Do you see? So in 8 positions, we have to fill in 4 spaces. So you could do 8 factorial over 4 factorial as your solution. So in the terms of factorial notations, we could write like this. Now, therefore, we get total choices as 105 times 8 factorial. We'll learn about choose combinations later, and so I'm not getting into 8C4. We have to choose 4 S's from 8, right? It's kind of a group. So we are not using that convention, but we can go with our permutation, which is 8 factorial times 4 factorial are the ways for placing s in between, right? So s in between. So if you put them in between, they are separated. So multiplying with 105, which was the arrangement of all of the letters, right, gives us the answer 7350. It is very important to note that this is not 34,650 take away 840, right? So this is a different case. So I hope with this you understand how easy it is, if you understand the concepts, to find the total number of arrangements when things are put in order. They could be distinct, they could be repeated, right? So all different combinations we have seen, they could be arranged in a row, or they may be placed in a circular form. All these cases can be easily taken care of. So with that, we end our lesson on learning about finding the number of combinations, or you should say strictly arrangements, when things are placed in order. We call that permutation, right? So with this, let's end, and we'll take up combinations in our next video. I hope you find it interesting and useful. If you really want to learn from me, you can send an email to the given address here and we can discuss. Thanks for your time and all the best.